Equilibrium. 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 Equilibrium.
Hello, most studious students out there in ChemCast land. This is Mr. Cochran here to talk about equilibrium. In this short podcast, we'll talk about what an equilibrium constant represents for a reversible chemical reaction. We'll discuss how we can write an equilibrium expression given a chemical equation for a reversible reaction. And we'll talk a little bit about what equilibrium values tell us about a reversible reaction. So let's deal with the first question. How do we quantitatively represent the equilibrium in a reversible chemical reaction? The answer to that question is to write an equilibrium expression represented as KEQ. The K in KEQ represents a constant, as it often does in science. The EQ represents equilibrium, hence equilibrium constant. Why can we calculate equilibrium as a constant? Well, you know, at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So the relative concentrations of products to reactants remain steady or constant. Therefore, we can calculate equilibrium constants. KEQ for a reversible reaction is a number expressing the quantitative relationship between the mathematical product of the molar concentrations of the products divided by the mathematical product of the molar concentrations of the reactants, each raised to the power of their coefficients. What? I think it might be easier if we just write the KEQ expression for this reversible reaction where A of A plus B of B yields C of C and D of D. You can tell this is a reversible reaction by the double arrow between the reactants and the products. What you see here is the molarity of C raised to its coefficient times the molarity of D raised to its coefficient, C and D being the products, divided by the molarity of A raised to its coefficient times the molarity of B raised to its coefficient, A and B being the reactants. Let's take a closer look at what each one of these symbols represents. The brackets represent the molar concentration, or moles per liter. Capital A represents substance A, and the small a represents the coefficient of A. The coefficient is the number that we would use to balance the chemical reaction. So in its essence, really, KEQ represents a ratio of the concentrations of products to the concentrations of reactants. Therefore, if the KEQ is greater than 1, then the products are favored at equilibrium, or will have more product at equilibrium. If the KEQ is less than 1, then the reactants are favored at equilibrium and will have more reactants at equilibrium than products. So now let's write an equilibrium expression for this reaction between nitrogen and hydrogen gas, which will go through a synthesis reaction to produce ammonia. You can see in this reversible reaction that one nitrogen molecule will react with 3 hydrogen molecules to form 2 molecules of ammonia in a reversible reaction. Therefore, the equilibrium expression for this reaction will look like the following. The KEQ, or the equilibrium constant, will equal the molar concentration of ammonia raised to the second power divided by the molar concentration of nitrogen times the molar concentration of hydrogen raised to the third power. This shows what we would call the equilibrium expression for this reversible reaction. So once you know how to set up an equilibrium expression for a reversible reaction, then we can enter the molar concentrations of the products or the reactants and solve for the unknowns in the equation and or the KEQ. Something to make note of when you're writing equilibrium expressions is that solids and liquids are not included in equilibrium expressions as their concentrations remain constant and they don't really affect the equilibrium values. So it's important to pay attention to the physical states when setting up your equilibrium expressions. Well, that's about all we have time for today. This is Mr. Cochran saying equilibrium.
It's dynamic.
Music is Start the Commotion by the Wise Guys from the Zoolander soundtrack.